An election can produce three candidates who all lose to each other. Not tie. Lose. Put the first candidate against the second, and the second wins. Put the second against the third, and the third wins. Then put the third against the first, and the first wins. The voters haven't changed their minds. We haven't counted anything twice. The result is a perfect loop. Here it is happening. 9 voters rank 3 choices. 3 prefer orange, then teal, then purple. 3 prefer teal, then purple, then orange. And 3 prefer purple, then orange, then teal. Compare orange with teal. 6 voters put teal higher, so teal beats orange, 6-3. Compare teal with purple. 6 put purple higher, purple wins, so purple must be the strongest, right? No. Compare purple with orange. 6 voters prefer orange. Orange wins. Teal beats orange. Purple beats teal. Orange beats purple. Every candidate has a majority victory, and every candidate has a majority defeat. If you ask this electorate to choose the best option using one-on-one majority votes, there simply isn't one. And this isn't caused by anyone voting irrationally. Each person has a completely tidy ranking. No voter says orange is better than teal. Teal is better than purple. And then somehow purple is better than orange. The loop appears only when their sensible rankings are combined. That's the part I want to get hold of. How can 9 straight lines of preference assemble themselves into a circle? The circle appears because a majority isn't one fixed group of people. It changes with the question. When teal faces orange, the teal first voters join the purple first voters. That's 6. When purple faces teal, the purple first voters join the orange first voters. Another 6, but not the same 6. And when orange faces purple, the orange first voters join the teal first voters. Each contest recruits a different coalition. That's the mechanism. Nobody's preference bends into a loop. The winning coalition rotates around the electorate. You can picture the 3 groups passing a 2/3 majority baton. The first 2 groups defeat one option, then the last 2 defeat another, then the outside pair defeats the remaining one. Majority rule is behaving perfectly in every individual contest. It's the contests together that don't behave like a ranking. Mathematicians call the property we're missing transitivity. If I rank orange above teal and teal above purple, transitivity says I should rank orange above purple. Each voter does. But majority preference doesn't have to. That distinction is easy to miss because we talk about an electorate as if it were one large person. We say the country prefers this, the committee wants that, the audience chose something else. Grammatically convenient. Mathematically dangerous. The collective has no single mind whose preferences must stay consistent. Fine, so a loop is possible. But our example was suspiciously neat. 3 equal camps, perfectly rotated rankings, 6-3 victories everywhere. Maybe this is just a carefully balanced mathematical toy. If one voter changes position, does the whole ridiculous thing collapse? One changed voter doesn't necessarily save us. Suppose a single voter in the orange first camp swaps teal and purple. The ranking becomes orange, purple, teal. Orange still beats purple, now 7-2. Purple still beats teal, 6-3. Teal still beats orange, 6-3. The loop survives. One edge merely gets stronger. We can disturb other rankings too. The margins change, the symmetry disappears, and the cycle can remain. So this isn't a numerical coincidence balanced on one voter. It occupies a real region of possible elections. How much of a region? If voters independently choose among all 6 possible rankings of 3 candidates, with each ranking equally likely, cycles don't dominate, but they don't vanish either. As the electorate becomes large, the probability approaches about 8.8%, roughly 1 election in 11 under that simplified model. Now, real voters don't choose rankings by rolling 6-sided preference dice. Political opinions correlate. Candidates can lie along a left-to-right axis, and that structure often suppresses cycles. Consequential caveat. But issues aren't always one-dimensional. One candidate may be preferred for cost, another for safety, another for speed. Different groups can weight those features differently, which is exactly the raw material a rotating coalition needs, so the loop isn't guaranteed, and the random model isn't a forecast. It proves something more basic. Increasing the number of voters doesn't wash the problem away. The margins become more stable while the collective cycle remains possible. Alright. If there isn't a candidate who beats every rival, an election still has to print somebody's name at the top. Perhaps the voting method can resolve the loop fairly. Let's try the most obvious thing. Hold the pairwise contests one after another. Pairwise contests do resolve the loop. They also hand an extraordinary amount of power to whoever chooses the order. Start with orange against teal. Teal wins. Now teal faces purple, and purple wins the final. Purple becomes the official choice, but put teal against purple first. Purple wins that round, then loses to orange. Now orange is the official choice. And if purple faces orange first, orange advances, and teal beats it. Teal wins. Same voters, same preferences. 3 possible winners, selected entirely by arranging the questions. The agenda doesn't merely affect the process. Inside a cycle, it can determine the result. Notice the rather awkward feature here. The eventual winner loses one of the possible head-to-head contests. We just avoid holding that contest at the decisive moment. A chairperson who knows the preferences doesn't need to change a single ballot. They only need to choose which comparison happens first. This is why a cycle isn't merely philosophical trouble about the word best. It creates a practical steering mechanism. Committees use motions, amendments, runoffs, and elimination rounds. Whenever earlier results decide which later comparisons are available, the bracket becomes part of the voting rule. Could we escape by ignoring pairwise order and simply counting first choices? In our original election, all 3 candidates received 3 first-place votes, a tie. Disturb the number slightly and plurality will pick someone, but it throws away everything below first place. A candidate narrowly ranked second by almost everyone can lose to somebody loved by a minority and hated by the rest. So let's keep the full rankings and award points instead. That feels harder to manipulate. It also creates a new problem. How far apart are first, second, and third? Give 2 points for first place, 1 for second, and 0 for third. In our symmetric election, each candidate gets 9 points. Another tie. That's not surprising. The entire example rotates perfectly. But the important change is that points force us to measure preference, not merely order it. Is moving from third to second worth exactly the same as moving from second to first? The ballots never told us that. We inserted it. Change the scale to 10, 1, 0, and first place intensity dominates. Change it to 2, 1.9, 0, and broad acceptability matters much more. Both systems use every ranking. Both produce a crisp total. They can choose different winners because the totals contain assumptions that aren't present in the rankings themselves. There are excellent reasons to use scoring rules. The familiar 2, 1, 0 version for 3 candidates is the Borda count, and it rewards candidates who place consistently well. But it cannot manufacture a uniquely correct answer from information voters never supplied. Perhaps elimination could do better. Count first choices, remove the candidate with the fewest, transfer those ballots to their next choice, and repeat. Now the lower rankings matter only when needed. Watch what happens near a threshold. One extra first choice vote can determine who gets eliminated. That changes which ballots transfer. Those transferred ballots can then decide the final by a large margin. A tiny movement at the first stage reroutes the whole election. Worse, adding support to a candidate can sometimes make that candidate lose under certain elimination rules, because the extra support changes who survives to face whom. The broken assumption is more severe than I first expected. More votes for you should not be bad for you. The property has a name, monotonicity, but the name matters less than the failure you can now see. Are we just shopping through flawed rules then? Surely there must be one clever counting method that respects every reasonable demand. There isn't, and now the circle from the opening becomes part of a much larger obstruction. Suppose we want a ranked choice system with at least 3 candidates to satisfy a few demands. If every voter prefers orange to purple, society should rank orange above purple. The result shouldn't be dictated by one fixed voter. And the social ranking between orange and purple should depend on how voters rank those two, not on whether teal enters, leaves, or changes its hairstyle. That last condition is called independence of irrelevant alternatives. It sounds almost offensively reasonable. If we're comparing orange with purple, why should teal matter? Arrow's impossibility theorem says that no rank order voting system can satisfy all those conditions while always producing a complete transitive social ranking. Something has to give. The theorem isn't saying all voting systems are equally bad, or that elections are pointless. It says every method makes a trade-off, points at assumptions about distances between ranks. Elimination makes paths and thresholds matter. Pairwise methods may expose cycles. Other systems relax some condition, restrict the kinds of preferences allowed, or accept that the output may not be one clean ordering. And there is a lovely, slightly brutal reason. The theorem feels unavoidable after our example. Individual rankings contain only local comparisons. The voting system must compress many of them into one collective ranking. But the majority relation can already contain a circle. To straighten that circle, the rule must override at least one majority comparison, consult information outside that pair, leave the result incomplete, or grant somebody special power. There isn't a fifth move hiding under the table, so which compromise should we choose? That isn't answered by mathematics alone, because the choice depends on what kind of failure matters most in the institution we're building. For a small committee, pairwise discussion may be valuable even if it reveals a cycle, because the cycle tells the group something real. Its coalitions change from issue to issue. The committee can negotiate, gather more information, or admit that no option has general majority support. For a public election, stability and resistance to strategic control may matter more. A method might choose the candidate with the strongest pairwise record, the smallest worst defeat, the highest score, or the safest elimination path. Those aren't different ways of discovering a hidden winner. They're different definitions of what winning should protect, and voters can behave strategically under many rules. In plurality, you may abandon your favorite because they seem unlikely to win. In a point system, you may exaggerate the distance between candidates. In elimination, you may worry about which opponent survives. The counting rule changes the tactical landscape because it changes which information on your ballot can hurt or help. This sounds bleak until you turn it around. Voting mathematics isn't proving that collective decisions are hopeless. It's preventing the rule from disappearing behind the result. When someone says, the voters chose this, the useful next question is, by which comparison, which scale, which elimination order, and which compromise? Look again at our 9 voters. Every one of them gave us a clear, consistent answer, yet teal defeats orange, purple defeats teal, and orange defeats purple. The circle isn't an error in the count, it is the count. The opening picture now means something different. It doesn't show 3 terrible candidates or 9 confused people. It shows the moment individual preferences stop behaving like one giant preference. Any system that names a winner must cut that circle somewhere. The winner is real, but so is the cut.